Okay, we should be good now. Okay, type another comment if it's still not loud enough. Okay, sure. I'll quickly repeat what I said. For the first one, it's just the family-wise error rate. And the fact that it says paired t-test has nothing to do with the family-wise error rate. The number of tests you perform, whatever those tests are, they can even be a combination of different kinds of tests, so t-test, chi-square test, whatever. That dictates the chance of at least one false positive among all the tests that you do. So it's just 1 minus alpha to the power of k. Well, alpha is mentioned in the question, and k is the number of tests, which is 10. So it gives you a chance of a little over 40%, which is really, really large. Okay, second one, first you just have to copy this chunk and run it in R, and that will store a vector called p-values, and then you just run the p.adjust function on p-values once with a Bonferroni as a method and once with the FDR as method. Yeah, and this is just a way in R to ask which ones are less than 0.05. But you can do it by hand. Okay, then the important one. So, I think I skipped one, so let's have a look at that. Oh yeah, why are some p-values equal to 1 after correction? So yeah, that one is just because a p-value is supposed to represent a probability, the probability of finding this extreme result if the null hypothesis were true. And probabilities cannot be greater than 1 because with 100% chance something will almost surely happen, and there is no such thing as a 200% chance or something. So it's just a way to make sure that the p-value still makes sense in terms of interpretation. Yeah, the way that's done in the p.adjust function is that they have this p minus, which means across the whole vector apply this function the minimum of 1 or x times the number of tests. Yeah, so this is the Bonferroni correction, p-value times number of p-values, and this one just says it cannot be greater than 1. Okay, then we have the important one, which is the correct interpretation of a p-value. I make this a little bit bigger, and oh, let's not do that. And then I'd like to ask if anyone has an idea which one of these might be correct, or maybe you have an idea which one of these are not correct. Anyone wants to chime in? So there's 8 definitions given here. Anyone has an idea whether any 8 of these are correct or incorrect? Yes?
I think 7 is correct.
Okay, so she thinks the 7th definition is correct. The chance that the test statistic is this large or larger if the null hypothesis were correct. Yeah, that is the textbook definition of the p-value. It's a bit, yeah, unintuitive, but unfortunately that is what we're dealing with, which is a reason why some people don't like significance testing. So this is how you should interpret it. You assume that the null hypothesis is true, then you draw a sample, and that sample doesn't have an exact test statistic of 0 because it's just a sample and it has sampling error. So you accept that it will deviate to some extent from 0, but when it deviates a certain amount from 0, namely the critical value, then you say, okay, this deviates so far from 0 that I no longer believe the null hypothesis. And that gives you p, that is just the chance that you would get a test statistic this large or larger if the null hypothesis were correct. Okay, so that one is correct, but actually there are 2 correct definitions given here. So anyone able to identify the other one? Okay, anyone has an idea which of these are incorrect? You have a pretty good chance if you just guess that you have it right.
The 8th one is correct as well?
Yes, very good. So someone says the 8th one is correct. If the null hypothesis were true, sorry, let me select it, and the experiment were repeated a large number of times, then the p-value is the expected proportion of experiments with this large or larger tested. Okay, so this is a very, complicated way to phrase it, but yeah, again, a p-value is very often misinterpreted as just, oh, that's the chance that the null hypothesis is true. No, it's not. So this is the actual correct way to interpret it, because what you're really saying is if you would draw many samples from the null distribution, then you would assume a certain proportion of them to have a test statistic larger than this, and a smaller proportion to have a test statistic even larger than this, etc. So that is what the p-value is. In reality, we usually only have one sample. We don't keep sampling from the same population. But yeah, that is the value that a lot of empirical science is using to draw conclusions about yes or no questions. Okay, then I think the more interesting thing is, why are the other ones incorrect? So I've written down some things here, so you can read this later. I will upload this after this lecture. Yeah, so the first one says the chance of a false positive. No, that's incorrect, because the p-value is just a measure taken from your sample, and your sample is random. So it cannot possibly be the chance of a false positive. And actually, you define the chance of a false positive, because that is the threshold after which you're going to reject null hypotheses, and it's alpha. So it's a value you choose. Then the second one, the chance that the null hypothesis is false. Yeah, this sounds like it could be right, but it really isn't correct, because you start by assuming that the null hypothesis is true. And if the null hypothesis is true, then yeah, any p-value is as likely as the other, right? Because you're saying that, okay, null hypothesis is true, so I might have a t-value of 0, might have a t-value of 0.1 or minus 0.1, minus 0.2 or plus 0.2, etc. So you're saying that every p-value has an equal chance, and only the smallest 5% we're going to reject. So yeah, it could be 0.00001 by coincidence. That's how empirical science works. So you cannot possibly interpret it as something about the null hypothesis. Then the third one, the chance that the null hypothesis is correct. Yeah, so this is also not the right interpretation for the same reason as the previous one, because you start by assuming it's correct. So you cannot first assume something is correct and then say, and therefore this statement is the probability that it is correct. Then you would have to start by not assuming that, and then build evidence for the null hypothesis. That's not something you can do with the methods we explained. It is something you can do with Bayesian statistics, but that is, that involves a lot more math, and is just in general not really a beginner's topic, so we don't treat that in this course. Then we have 1 minus the chance the alternative hypothesis. Yeah, it's just a different way of phrasing the other ones. It just doesn't give you a chance that one or the other hypothesis is correct or false. That's not something the p-value can do. Finally, the probability results arose by chance. I think this is the most quoted wrong interpretation of the p-value, because any result is by chance. Also, if if the null hypothesis is incorrect. A sample is a random sample, so this wording is just imprecise and therefore incorrect. Also, you don't know if the null is true or false, and therefore you cannot say that this is the probability the results arose by chance. It's essentially the same as saying the probability the null hypothesis is true, which is incorrect. And the other two are correct. I know that they're not easy interpretation, and people always try and find some easier way to phrase it, which makes sense. I would do that for anything you learn. But unfortunately, the p-value has a very specific interpretation, and well, especially the first one I wrote down here, this one, I think is the shortest way to write it, such that it is still correct. So yeah, if you still find it difficult, I would say look up more about this. There are a lot of good questions on cross-validate about this interpretation, but in any case, memorize this. This is really important. Okay, then the last one, I'll just show the picture. So yeah, this is from XKCD, which has a lot of nice pictures from chemistry, biology, physics, and math, and therefore statistics. And the idea is that someone is going to find out whether one thing causes another thing. And the answer is okay, if we do a t-test, we didn't find significant effects, right? So we didn't find evidence to support your hypothesis. And then, okay, well, maybe it's something else. And then they look again. No. And then maybe they look again. Maybe that's what it is. And then finally, after many, many, many tries, then the incorrect wording of confidence interval in this case is reported, namely that green jelly beans are linked to acne. with 95% confidence and only a 5% chance of coincidence. Now, this is why the correct interpretation of the p-value matters, because if you could use any of these interpretations, then this statement would be correct, but I hope that intuitively the statement is not correct, right? So what went wrong here in this experiment? What should they have done?
They should have used a correction because they're using the same sample over and over again, so they're giving a chance of getting false positives.
Yeah, that's almost correct. It's a bit more subtle than it. This is a very nasty problem that we are not going to solve in this course. If you keep studying the same thing, even with new samples, every new sample has its own chance of a false positive. So this is actually an image about a debate about frequentist statistics. So everything we've learned so far is called frequentist, where people say, well, you should not only correct for the number of p-values in your own experiment, but you should correct for any study that has been done on that effect. Because if you keep doing studies on it, you're going to find something that is incorrect. And yeah, there's no real good way to settle that debate, whether you should or should not correct for previous studies. I think that you shouldn't, and that you should just accept that a certain proportion of articles will have false positives in them. But there are people who say that that is not right and you should correct for everything. But yeah, if you keep applying more multiple testing correction to everything, then your power will go down and you'll need larger and larger sample sizes to ever demonstrate anything of interest. Was that clear? And is there any other question you would like to see the answer to right now? Okay, if not, then we're going to go to the lecture of today by Levi. Okay, I will keep an eye on the chat so you can just
Perfect.
use that.
Just one question before we start.
Oh, could you do it over here so people can see you?
Yeah, sure. Hi guys. Frans, maybe one little question to you. I think it would be nice if at some point I were able to write a few things on the whiteboard. Is it also possible for the people at home to see that?
Not easily, because that is connected to a different computer.
Okay.
Which is of course very future-proof, which is why I love the university systems. But you can draw here.
Okay.
Yeah, if this is, I hope this is okay. Yeah?
Okay, so let's see, this is...
Yeah, just go to Paint on this one.
Okay, yeah,
Yeah?
perfect.
Oh, sorry, there's one question. Why not use all the samples in one test instead of many tests? Yeah, of course, that's a good idea. You would want to use all your samples at once to draw one conclusion about all your hypotheses, and then still correct for multiple test correction.
Okay, I guess I will get started then. I will get off this one. Good morning, everyone. It's very nice to see all of you. Very nice to be here. Thanks to Frans for allowing me to give this lecture. So, my name is Levi Winkelman. You might know me as the teaching assistant. I'm going to give this lecture about Anova, which is short for Analysis of Variance. And I think this might be one of the most difficult topics so far. So please, if you have any questions, don't hesitate to interrupt me. Also via the chat, I'd be more than happy to stop for a while and answer your questions. Also, if I go too fast, please let me know. So the lecture slides that I'm using are actually from Frans Rodeburg as well. I have changed them a bit to kind of give it my own twist and to make things as intuitive as possible to me. But if you'd like, you can also still watch the lecture of Frans. He already recorded it, and you can find it either on YouTube or on Brightspace. Okay, so maybe it's nice if I put up the presenter view. Okay.
Presenting notice. Let's see. so maybe. No. Okay, so what we can do instead. Strange. Oh yeah, this place. And there we are.
Great.
Duplicates. Okay. Is that okay? Or?
Yeah, I kind of like to have my notes here, but I guess
Okay.
I guess it's fine.
Okay, if
I'll
you
just
can
try.
always just do it in the small
Yeah, in
view.
the small view. Okay, perfect. Okay. Okay, so the first thing, why should you care about ANOVA? So why are we giving this lecture? I think it's always important to know what you're going to study before you start. Well, previously you studied the t-test, and the t-test is a very powerful tool. So if you have two groups and you want to compare their means, you perform a t-test. And ANOVA is kind of an extension to the t-test, and it's one of the most widely used statistical tests out there. So I think it's a very nice addition to your statistical tool belt. Okay, so this lecture will be divided into 3 parts. First, I will give you a small overview of what ANOVA actually is and how it works. There was no question?
No.
Okay, great. Then I will run through an example. We also have some R code, so I will show you that. And the third point is a two-way ANOVA, multi-way ANOVA, so different kinds of flavors, so to say, of ANOVA. Okay, so as I said, an ANOVA is a model for comparing any number of group means. So you could consider it as a generalization or an extension to the t-test, which compares two group means, but instead we can compare any number of group means. So I might be able to draw that. So if we go back, I want to do like a quick recap of the t-test. You have, for example, two groups, both with its own mean and both with its own standard deviation. And you want to know what the difference is between these means. And to assess this difference, we use something called the T statistic. And if you remember correctly, the formulation of the T statistic is the difference in means. So we call this mean x bar 1 and this mean x bar 2, for example. Excuse me for my poor writing skills. The T statistic is then x bar 1 minus x bar 2 divided by the standard error. Does any of you remember what the standard error is in this case?
Measurement of uncertainty.
Exactly, a measurement of uncertainty. So if our standard error is very large, then the standard deviation of these group means are big. So we are uncertain in the difference between the means. Okay, so how do we go from this formula, the t-test, to the ANOVA? Well, we can no longer use this formula because, for example, in an ANOVA, I will erase this first. Oh, that's probably not the best way of doing it. Maybe like this. Okay, I'm not very familiar with this tool. What if we do it like this? Frans?
Sorry about that. Okay, so these are tools. This is fill. Is this what you want?
Yeah, perfect.
Okay.
Okay, great. So, if for example we have 3 group means, I will try to draw that out. Okay. I'm drawing with white, so if I do this, then it should be fine, right? Yes. Okay, so let's say we have 3 group means. then we also have a bunch of different comparisons we can make. So we can assess this difference, but also this difference, and also this difference. So how do we do that? Well, for that we use the Anova. And an Anova basically consists of two parts. First you do an Omnibus test, and the Omnibus test kind of tells you, is there any difference between all the group means at all? And then you do a Postdoc analysis if you get a significant result for the Omnibus test. So if there is a difference between all the group means, if they're not all pooled from the same population, then you can check which of the means differ from one another. And in this Postdoc analysis, there's two ways to do it. You could either do a bunch of t-tests, because you're comparing group means. So if you're comparing two groups again, you could use a t-test again. You should compare for multiple testing if you do that. And another way, which is especially for the Anova, is the Tukey test. So let's go to the Omnibus test. We see the zero hypothesis over here. So we have a number of groups, and let's say this number is k. Then the null hypothesis is that the mean of group 1 up until the mean of group k are all equal. And I always found this a bit funny or a bit weird, because back when I studied biology, I thought, okay, how could this be? Because we're comparing means, so why are we calling this analysis of variance instead of analysis of means? Well, that actually has to do with the definition of Anova. So if we remember, the formula for the t-test was the difference in means divided by the standard error. Now, for the F test, so that is the test statistics for the Omnibus test, we do something kind of similar. Instead of looking at the difference between two means, we look at the average distance or the average difference between all the means. And the average deviation, that is pretty much the definition of variance. So that is why we call it analysis of variance. And what we have in the denominator of the F test, that is the residual variance, that is actually quite similar to the standard error we had in the T statistic as well. So the larger the F value you get from this Omnibus test, the greater the evidence against the zero hypothesis. And the logic is, if the group means do not differ, then their variance is also zero. So this way we can compare all the means at once without a multiple testing issue. Okay, so here Frans provided me with a very nice graphic. What we see over here is we have a big probability density function, and this probability density function is comprised out of three different groups. Now you can see if the means are far apart, the probability density function has this weird non-normal shape, and that is because like the means are far apart. But if the group means come closer, the total probability density will start to look more like a normal distribution, implying that all the samples are from the same population. Now, the full calculation of the F statistic looks like this, and this may look like a very difficult formula, and don't worry, you don't have to know this by heart, but I do think that if you understand what it's saying here, that you're in pretty good shape to understand what the Omnibus test really is all about and how the F statistic works. So I will try to run through all of this. So what we see over here, y bar, that is the mean of all means. So if I go back to my drawing, we have three groups. Let's say that this group is a bit more to the right, or is a bit closer to the third mean than to the first mean. Then the mean of all means would be about here. So we have the mean of all means, and we subtract each single mean from the mean of means. We square that difference and we sum them all up together. So what we basically do is we take the squared difference between this mean and the mean of means, this mean and the mean of means, and this mean and the mean of means. We take them all together. Then we divide by our degree of freedom of the number of groups. So that is the number of groups minus 1. So here we have like the mean difference, the mean squares, you could say, because it's a square difference. Then in the denominator, we have a formula that looks a bit similar. We also divide by the degrees of freedom, which in this case is the number of observations minus the number of groups. And here we have the sum of squares for the residuals. So we're looking at each group mean individually. Each observation is pulled from that group mean, so we calculate the difference between all observations and the group means. We square the difference. We do that for all observations within a group, so that is this part. And then we also do it for all groups. So here we sum over all observations within a group, and here we sum over all the groups altogether. So in words, you could say that the F statistics is the mean square difference from the group means to the overall mean divided by the mean square difference from the observation to their group means. Is there any question about this so far? No? Okay, great. Well, please remember that you don't have to know this formula by heart. I do think it's nice to know. But if you try to memorize a formula for the exam, for example, I would go to this definition. So F is the variance between the groups divided by the residual variance. Okay, so now we can apply this to our calculations. Let's say we run an Anova, and here you see the R code we use. So the function for Anova is AOV. This is our response variable, and the groups are noted as treatment. So we make an Anova model. We plot our, or we say we have a response, we have our groups, and you can also say that the response and the groups are from a certain data frame. But this part isn't really necessary if you specify these groups in your global environment in R. Yeah? Yeah, sure. Better like this? Okay, great. Okay, so if we go back to the last slide, we can see that the F is the mean square difference from the group means to the overall means divided by the mean square difference from the observations to their group means. And we can find these values over here. So the numerator is the mean square difference of the treatments. So the numerator should be 790.2, and the denominator is the mean squared of the residuals. So we go to mean squared residuals, that is 27.3. Now if we do that, we get a pretty large F value, and a large F value always implies a low P value. So this means that we have a lot of variance between the groups, and that the variance within the groups is relatively small. And if that is the case, then you will always get quite a high F value and a low P value. Now, how exactly is this F value related to your P value? Well, for that you need to look at the F distribution. So this is what the F distribution looks like. What you would expect if the null hypothesis were true is that the division that you make for the F statistic is close to 1. So you see that the probability density, given that the null hypothesis is true, is very high, around 1. And the further you go away from 1, the smaller the probability density becomes. And if you have an F value of roughly 29, you go looking over here, and then you look at the area under the curve for all values greater than 29. So the probability of observing an F value greater than 29 is represented by the area under the curve here. And you can see it is so small, this area under the curve, that it is like 7 in a million. It's super low. So we have strong evidence to suggest that these group means are significantly different. Okay, so in summary, kind of, in a population with three groups with identical means, there is this chance of observing an F value as large as this one. And I think there might even be a few zeros missing here because the p-value was very low. So yeah, this chance is really small. So we stop believing in the null hypothesis and conclude that there is a difference between the group means. So probably your samples are not from the same population. Okay, now if that is the case, our omnibus test is significant. So we will perform a postdoc analysis. And you have fitted your Anova model. And with this Anova model, you can perform the postdoc, in this case, the Tukey test. So the formula that we will use is Tukey HSD. HSD stands for honest significant difference. And then we put in the model that we fit, so Anova. You can then print the postdoc, or you could simply leave out the arrow and just directly put in Tukey Anova. And this is the result that we get. So we are looking at all the differences between all the groups. So in this example, we are looking at 2 medicines versus a placebo. And here you can see the difference between the 2 medicines themselves. The adjusted p-value is above 0.05. So we don't have enough evidence to suggest that the 2 medicines have any different effect. But if we compare the placebo to each medicine independently, we get a significant p-value. And please be aware that if you're doing a Tukey HSD, you are already correcting for multiple testing. So there's no need to do that again. But if you're doing a t-test, then you should do multiple testing. Okay, and the interpretation of the Tukey HSD is basically the same as the t-test. Also, these tests are very similar, but we'll get into that a bit later. So, one more note about the Anova versus the t-test. If you do not need every comparison to answer your research question, then Tukey HSD will waste your power in correcting for the test that you're not interested in. So what do we mean by that? Well, if we think about the formula for the t-test again, we divide by the standard error. And this standard error is always computed by the 2 groups that you're interested in. Now, if you're doing an Anova, you have multiple groups. And even when you're comparing only 2 groups, you are still calculating the standard error over all the groups. So that is basically the difference between the Tukey HSD and the t-test. But for the rest, they're super similar. But if you're only interested in a few comparisons, then do the t-test. Otherwise, do a Tukey HSD. And in our case, we are actually interested in everything. So a Tukey HSD makes more sense because first, we would like to see, are both the medicines effective? But we would also like to know, is there a difference between the medicines? Is there one medicine that works better than the other? Okay, so what to take away from this? First, you need to recognize what is shown in the output. So if you get an output like this, you should be able to interpret it. I think interpreting our output is also very nice to know on the exam. Second of all, know what to look for when you're drawing conclusions. So what do the mean squares mean? What does the F value mean? How is it related to the P value, for example? And know what your evidence really means. So the P value, confidence intervals, how do you interpret them? Okay, so this was the end of part 1. I think this was, yes. So if you're doing a T Statistics, I'm not really sure if you can actually see the sample size from the output of a T test. Do you know that, Frans?
Yeah, so for equal variance T test, you can just count the number of degrees of freedom and add the number of means estimated. So
No.
1 extra for one sample T test, 2 extra for 2 sample T test.
Mm-hmm.
For Anova, could you show the Anova tag one more time?
Yeah, sure.
Omnibus test?
So this one?
The Omnibus test.
Oh yeah, of course.
Yeah, so
yeah.
here we see that you have 15 degrees of freedom for residuals and 2 for treatment. And you should be able to see from that, okay, if you have 2 degrees of freedom for the treatment, then apparently there were 3 treatments. And if you have 15 degrees of freedom for the residuals, then apparently there were 3 plus 15 equals 18 samples.
Yes.
So for the other numbers, you don't have to do it correctly.
Okay, thank you very much. Okay. So yeah, I think this was probably the most difficult part of this lecture. Are there still any more questions about this? No, Frans, also not in the chat? Okay, great. Yeah, well then I suggest we just continue on. So we will now run through an example of a one-way ANOVA and how to include it in R. So there's always 3 steps that you should do if you are performing an ANOVA. First is the diagnostics, then the Omnibus Test, and then a Postdoc Analysis. So usually that would be the T test. Okay, so in this example, we already kind of looked at this example actually. We measured the systolic blood pressure of 18 hypertension patients. And hypertension patients pretty much have a very high blood pressure, that's what it means. We divide these 18 patients into 3 groups. So 3 groups of 6. 6 of them undergo a treatment by thiazide, which is one medicine. 6 of them undergo a treatment by calcium channel blockers, another medicine, and 6 of them get placebo. Now, in a certain period of time, we measure their blood again, and then we see whether these treatments had an effect or not. So with an ANOVA, we can answer the following questions. Is there any difference in mean systolic blood pressure among the groups? So that would be the Omnibus Test. And which groups differ significantly? So that would be your postdoc. Well, the first thing you should do is always enter your data in R. And you could either do that just by filling in the values by hand. It's probably a bit cumbersome if you have a large data set, but you could do that. Another way is to read in your data from an Excel file. So the function that you would use for that is read.csv. And a CSV means a file that has comma-separated values. So that means if you are translating it to like an R data frame, then the commas in your original file will be used to separate the different columns. And if that is what you're doing, you should be careful when you have, for example, a Dutch version of Excel, because then maybe a comma does also mean, like that could also be used as the decimal separator. So in the Netherlands, we say, for example, instead of 18.3, 18,3. And if you have a file like that, so with Dutch settings, you shouldn't use the read.csv command, but the read.csv2 command. That would work as well. Okay, so suppose we read in the data correctly. We could then make the different treatments, so the groups. And what you basically do is that for each observation, you give the group that it belongs to. So first we want 6 times thiazide, then 6 times CCB, 6 times placebo. So you could also use the rep function. I don't know if you used it before, but this also works. This function stands for generate levels. N equals 3 means there's 3 different groups. K equals 6 means there's 6 observations per group. And the labels are thiazide, CCB, and placebo. Now, if you have that, you can combine that in a data frame. It's not necessarily, you don't necessarily need it for the Anova, but it could be nice for yourself just to have an overview. Okay, and once the data is read incorrectly, it is always nice to get a quick view of what the data looks like before you start to perform anything. That way you can see if the data is read incorrectly, but you can also already get an idea of where there might be differences. So then later on, if you perform your Anova and you have like the outcome, you can go back to this plot and see, okay, does this difference that we see make any sense? And if we look closely at this box plot, we can see that both medicines deviate quite a bit from placebo, so we expect to find a significant difference over there. And we also see some difference between thiazide and CCB, but whether that's significant, I couldn't really tell from this, so there it is nice that we have the test. Okay, so then after we visualize the data, we can perform the Anova. This is the function that we saw before actually in the output. So we make an object, we call it Anova, and it uses AOV, so that is the function you use to perform an Anova. SPP, so the systolic blood pressure, that is our outcome. And we look at the different groups, which are treatment. And here we specify where the data comes from. So the data is from data frame. Okay, then for model diagnostics. In descending order of importance, there are 3, maybe 4 assumptions that should be met if you do Anova. So the first one is that measurements are independent. Now, what does independent measurements mean? It means in this example that, for example, you don't use the same patient multiple times and treat all these observations as being equal. So if you have multiple measures of one patient, you shouldn't just put them all in the Anova. That would be a violation of one of the most basic assumptions. Yeah, if measurements are independent, that is also always a bit tricky, because as a statistician, you can never really be sure if measurements are truly independent if you only get the data set. So that is really something that you have to take into account when you're setting up your experiment. So yeah, that requirement just has to be met. Then the second one is that the deviations from the group means are normally distributed. So that basically means that, well, if the groups are all normally distributed, then often the residuals are also normally distributed. So you have to take that into account. And the third one is that the group variances are equal. Okay, so here once again, yeah, cannot be checked through diagnostics. Yeah, so whether measurements are independent, you cannot see from your data, and you can also not visualize it from diagnostics, unfortunately. But all the other ones you can visualize. And there's also one other thing to take into account, and that is that you don't include any significant outliers. Now, outliers may occur. Sometimes your data is just weird, but yeah, it is always nice if you can identify an outlier to go back to your data and see if something might have happened. Maybe ask the people who performed the analysis, or who performed the experiment, excuse me. Okay, so how do we visualize all these assumptions that we are trying to meet? we can do that with the following plots. So these are the 4 main plots that we use to visualize it. Here we have some R code. I will not go through all of it. You can just pull it from the slides if you want later. So here we have the first plot, which is residuals versus fitted values. And it takes a look at homogeneity or variance. So here we see all our groups. So this is the first group, second group, and third group. And if there was a heterogeneity in variance, so if the variance would maybe increase or decrease, then you would expect that in one group, for example, all the observations are close to each other, and they get progressively larger as the fitted values increase. So fitted values, does anyone know what a fitted value is? Okay, maybe that's good to know. So if you're doing like a linear model or an Anova, then the fitted value is like the expected value. So if in a certain group the expected value is very high, then the fitted value is very high. So here we have only 3 discrete time points for the fitted values, and these are pretty much the group means. So yeah, here we can see that there is no good reason to assume heterogeneity or variance, because as we can see, the spread doesn't really increase with the fitted values, and this red line remains pretty much constant. What we could also do is that we make this residuals all positive. So that is what we do on the scale location plot. So it's actually pretty much the same as here, but instead of just using the raw residuals, we transform them so that they all become positive values. Okay, then we have the assumption of normality, and we check that with the QQ plot. So if the data is normally distributed, you expect all the observations to be roughly on this line in the middle. And here we have the 95% confidence interval. And a rule of thumb, if you're doing a QQ plot, is that the observations in the middle are more important than the observations on the outside. And that's also the reason why the QQ plot gets larger confidence bounds once you're moving away farther from the middle. Now, there doesn't seem to be any big deviations from normality. All the points seem to fall quite nicely within the 95% confidence interval, and there's no weird shape. It does look kind of like a straight line. This plot is to evaluate outliers, and for outliers we use the Cook's distance as a measure, and we can see that all our observations have a Cook's distance that is lower than 0.3. So this Cook's distance is basically a combination of 2 things. It is the difference from the mean of an observation, and also the leverage. So how influential is a certain point? And a rule of thumb here is that if an observation has a Cook's distance that is higher than 0.5, then you should take a look into it, like maybe something weird is happening. And if the Cook's distance is higher than 1, then it's really a statistical outlier. So that might be problematic for your data. Okay, so this was, yeah, we covered quite a few things. As we saw in our plots here, the data that we ran through meets all the assumptions quite nicely. But what does it look like if the assumptions are not met? So that brings me to the next slide. Okay, here we see 4 plots, and I would like you all to take a look at this and to think which of these plots shows a violated assumption. If you know it, please raise your hand. Yes? Okay, very good. And how do you see that?
Because the residuals do not all fall within the 95% confidence interval.
Exactly. Well, sometimes if a point falls outside of the 95% confidence interval, It may not always be a big problem, but here in the middle of the QQ plot, we really see some big deviations. And also, it's not really a nice linear function that these points are following. It's more like a staircase. And if that is the case, usually there is something weird with your data. So this could, for example, be discrete data. In discrete data, so if you're measuring counts, for example, then you often see this staircase, and then you cannot use the Anova method. Okay, very good. Now we go to another one. So once again, I would like you all to take a look at these plots and raise your hand if you think you see what is wrong here. Yes?
Residuals fit the location as spread in the data.
Exactly, okay. So what violation is, or what assumption is violated then in that case? Yeah, so not variance per se, but like there is no heterogeneity of variance. So, or there is heterogeneity of variance, there is no homogeneity of variance. So indeed, as our fitted values increase, the variance increases. And we can also see that from the group means. So in this group, all the observations are quite close to each other. And as the fitted values increase, these observations get further and further apart. And the QQ plot also has a bit of a weird shape. It follows more of an S shape than like a linear trend. But that might also be due to this heterogeneity and variance. Okay, then I have one more. And I would like you all to think about this plot as well. Yes, please.
What's distance? We have one outlier that we call shouldn't include.
Exactly, yeah. So we have one observation, which is observation 17, which has a very high Cook's distance. And yeah, at a moment like this, it's always nice to look at your data. So for example, in the systolic blood pressure data, we could, for example, look at observation 17, and if you observe a blood pressure of 0 or a negative blood pressure value, then you know that it must be a mistake. So then you can take it out. So always take a look at the observation that you get, go through the data set, see if you find anything weird, and otherwise check with the people who run the experiment. Okay. It's 10:10 now. Maybe it's time for a little break. Yeah? Okay, so I would like you all to return in 15 minutes, if that's okay with you. And then I'll continue with the rest of the presentation. Yes?
What's the main difference between the first plot, like the residuals versus fitted, and the scale?
Okay, so guys, maybe one question for all of you. So I got a pretty good question, like what exactly is this difference between the residuals versus fitted plot and the scale location plot? Well, most statisticians I know only look at this plot because let's go to the example of heterogeneity of variance. Here you can really see that the observations get further and further apart from the mean, so the variance increases. If you transform all the residuals to become positive values, you get a bit of a better view of what the trend actually is. So here you see an uprising trend, which means that variation increases as the fitted values increase. So here the trend is a bit better visualized by the red line, but in this plot you can, like the distance between the dots is a bit more well expressed, so to say. Okay, thank you. That was it for now.
Want ze ook een Anova komen dus niet wel, maar blijkbaar zijn ze ook als filmpjes niet zo goede kwaliteit. Dus ik denk misschien niet. Ja, denk ik maar net als ik van hoor, maar
Where'd you receive it? I don't know. I just saw the email. I tried to go through the signal transaction.
Oh, yeah.
That's an exam. It's not an essay. That's an exam.
Why? They're genetic.
But you can be super good, but still get a bad grade for the essay because they didn't like it. That's not what I like it to be.
So how are you going to rank your essay?
Yeah, it should be what, 750 words? That's a lot. Here, you actually notice that.
But I know that I will keep your thesis like oh, you still making it right in the share. Do you thesis?
It's like, yeah, it's like ravioli, but with seafood inside, and they have like chocolate. I don't know, like, I was so happy from Mexico that I started eating, so I could just think
So your response to
Okay, guys, are you ready for the second part of the lecture? Okay, great. I'll see where we left off. Yeah. So, what to do when the assumptions are not met? Well, if the observations are not independent, then you could really not use the Anova method, because the standard errors, the confidence intervals, and the p-values that you get out of it cannot be trusted. In case of pseudo-replications, you could average over those observations. But what are pseudo-replications actually? Well, for example, in our experiment with the systolic blood pressure patients, we could say we don't only do one test where we take a blood sample and measure it, but we could measure it like 2 or 3 or 4 times maybe. But if you have all these different observations, you shouldn't just put them all into the Anova, but what you could do is average over these observations. So if you measure the blood value of a patient multiple times, then you could average for that person over all the blood values. Another case of independent data is repeated measures. So for example, you want to see the effect over time of a certain treatment. So maybe you give the patients a medicine and you look after 1 week, 2 weeks, and 3 weeks. Then that could be a very interesting experiment as well, but you cannot use Anova for it. What you could use is a mixed effects model, but that is something that will be covered once you do advanced statistics. So you will get that later. Now, if normality is violated, then what to check is whether normality was a reasonable assumption in the first place. So sometimes your data just isn't normally distributed. If there is another distribution that you can assign your data to, then you could consider a GLM and put in the distribution that you think the data comes from. And if you really can not make any assumptions about your data, you can also use a test that doesn't make the normality assumption, which for example will be the Wilcoxon test. But if you're doing the Wilcoxon test, you should also correct for multiple testing. Okay? If equal variance is violated, then you could consider transforming the response variable. So, for example, instead of looking at systolic blood pressure, we could look at the log or the square root of the systolic blood pressure, for example. You could also use a robust regression, that is a type of linear regression with weights, also that will be covered later. And Anova is still a valid approach, so if there is no equal variance, you could still use an Anova, but it's just not as efficient and not as good as when the variances are equal. So aim for equal variances, maybe consider transforming the response variable if the variances are not equal. Now, if there is a problematic outlier, you shouldn't just remove the outlier when you see that there is an outlier. Always go back to your data, see if there's anything weird. So, for example, a value that is theoretically impossible. And otherwise, just go back to your experiment, maybe your lab journal, see if something weird happened that day. Maybe ask the people who ran the experiment, something like that. And once again, you could use the robust regression. Okay, so for the Omnibus test, we continue with our example now. The Omnibus test has the null hypothesis that all means are equal. We use a significance level of alpha, which we usually set to 0.05. And to find the p-values and the f-values and the mean squares, we use this function, so summary, and then the variable that you assign the Anova test to. Now, we see that the p-value is very, very low. It's 7 in a million. And this is much smaller than alpha, so we reject the zero hypothesis, the null hypothesis. And if we reject it, we conclude that there is a significant difference between the means. Okay, well, since we reject the null hypothesis for the Omnibus test, we continue with the Postdoc analysis, and we run the Tukey HSD because we're interested in all the differences. So you do Tukey HSD of the Anova, and then you can print your results like this. And this is the output. So what we see over here is all the differences. So these values over here are the exact differences in means between the groups. And these differences come with a confidence interval, because you're never really sure if the difference between the means that you're measuring is the true difference between the means. There could be some sampling error, for example. And the uncertainty in this difference we express by a confidence interval. And here we see the lower and the upper bound of the confidence interval. And what you could take a look at is whether 0 fits within this confidence interval. Because if it does, then you cannot say with 95% confidence that this difference is indeed does indeed exist, because 0 is somewhere within that 95% confidence bound. And because 0 is between -2.5 and 13.16, we get a p-value that is above 0.05. And for the placebo thiazide and placebo CCB groups, we do see that both the confidence intervals don't include 0, and therefore we get p-values that are both above alpha. You can also plot this. So here once again we have the difference that we observed. And here we have the confidence intervals. So this is CCB thiazide. Once again, 0 is within the confidence bound. And here is placebo thiazide and placebo CCB. So this is also a nice visual way to put this. You can just plot the postdoc, which you did before, and remember postdoc was H-SD of the Anova. Okay, so a quick recap of all the steps that we took in the analysis. First, we read in the data. We fit the Anova. So AOV, that is the formula we use for it. We have the response, we have our groups. We can do a visual check, so we plot the Anova. Then we check the Omnibus Test. So with summary Anova, we can see the F value and the P value related to it. And then we can perform a postdoc analysis. Okay, so this was the end of part 2. Are there any questions about this? No? Okay, great. Then we will go to the third and last part of this lecture, and that is the different types of ANOVA. So what we did up until now was looking at the one-way ANOVA, and one-way ANOVA means basically that we're looking at one factor. So we have a certain number of groups, but these groups are all like different variants of a single factor. So here we have the treatment, which was either placebo or one of the two medicines. But you could also look at a different variable altogether, so maybe sex. So if you're looking at sex and the treatment both together, then you call it a two-way ANOVA. So yeah, so far we've discussed the ANOVA for a continuous outcome variable, a categorical explanatory variable, so treatment, but we can also use it for any number of categorical variables. So yeah, if there are two explanatory variables that we're looking at, two categorical variables I should add, then you call it a two-way ANOVA. And if there's more than two variables that you're looking at, you call it a multi-way ANOVA. So as I said in the example just now, we can also look at sex, so we can include that in our data set. So once again, here we have the systolic blood pressure measurements, we have the treatments, and we have all the sex data. So whether the patients were male or female. Now, how do you add this in R? It's actually not that difficult. Once again, you run the ANOVA function, so AOV. Then you put in the response variable that you're interested in. So in this case, systolic blood pressure. You say tilde, and then the treatment. So that is one of the groups that you're interested in, or one of the explanatory variables that you're interested in. And you just put a plus sign and then sex, so the other explanatory variable. You can then also specify the data frame where it comes from. So in this case, that would be data is data frame. Okay, we name this, what we did over here, the two-way. And once we do a summary of two-way, we once again get the ANOVA table. And this would be the Omnibus test for both categorical variables. So as we can see over here, we do have strong evidence that the treatments are different from one another, but we don't have any strong evidence to suggest that there is a difference in sex. So actually it doesn't make a lot of sense to do a postdoc for sex. Okay, but we could try it anyways. So here we do a postdoc, so Tukey HSD for the whole model, so two-way. And what you get is the same output that we got before when we ran the postdoc, but now there's also a separate tab which is for the sex. So we see the confidence interval here. So we do observe some difference between the means of males and females, but the confidence interval that belongs to this difference, it does contain 0, and that's why the p-value that we observe is above alpha. Now once again we can plot the data, and this is the data that we got before. So we say plot postdoc, and then we don't just get one plot, but for each categorical variable we get a plot. So this is the male-female difference. We do see some difference between the means, but it is not significant. If you have an Anova and you fit the model for 2 categorical variables, but you're only interested in treatment because sex is not significant in this example, then you can also run the postdoc for only one of the variables, or for a couple of explanatory variables, but not all of them. And the explanatory variables that you're interested in for the postdoc, you can specify those with the which argument. So here you say which is treatment. And once you do that, you can print the postdoc again, and then we got the same results that we get from the postdoc if we fit the Anova model with just treatment. Okay, here's another example of the multi-way Anova. So here we have a question: does adding a certain supplement to soil have any effect on the yield of a crop? So we're looking at nitrogen, phosphorus, and potassium. And with all these combinations, there is a specific yield that is associated to it. So once again, we can fit the model. So the multi-way is defined as the Anova model with response variable yield, and explanatory variables are nitrogen, phosphate, and the potassium. Now the data set that we use it from is NPK. And once again, we can run the postdoc analysis. So that would be Tucky HSD multi-way. If we do it, we get the output that is shown over here. And for each of the different variables, we get a confidence bound and a p-value. So as you can see, nitrogen is significant. We can also look at the confidence bound. So 0 is just outside of the range, but for phosphorus and potassium, 0 is within the confidence bound, and therefore the p-values are non-significant. Okay, now what would happen if, for example, nitrogen would have an effect, but only in the presence of some other supplement as well? So that might be the case, that nitrogen itself isn't very helpful in increasing the crop yield, but that the combination of nitrogen and phosphorus, for example, is effective. Well, you can check that by adding an interaction to the Anova model. Now, how do you include an interaction? We do that in R by specifying n colon p. So this part right here specifies the interaction between nitrogen and phosphorus. So this is the effect of having both nitrogen and phosphorus at the same time. If you're adding an interaction between 2 variables, then those variables should also be added separately in the model. So you cannot run this interaction without phosphorus, for example. So in this case, our function would be AOV, then yield, so the response variable, all the categorical variables, and the interaction of interest. Okay, so then with this new model, we can also perform a postdoc analysis. So once again, we do the Tucky HSD function on the one interaction, and we can print the results. And here we have so the results for nitrogen, phosphorus, and potassium on their own, so their own separate effects. And these are the combinations of nitrogen and phosphorus. So this would be adding just nitrogen. This would be adding just phosphorus. And this would be adding both, for example. Okay, now how about all the combinations of the two? So we have nitrogen, phosphorus, and potassium, but maybe we're not only interested in the interaction between nitrogen and phosphorus, but also in the interaction between nitrogen and potassium, and in phosphorus and potassium. So in that case, we could just put it all in the model. So for each explanatory variable that you're interested in, you just put a plus sign there. So we have n, p, k, and all the interactions. And then we can run a summary again, and we see all the different effects over here. So as we can see, the nitrogen does have a significant p-value, but for the rest, none of them is significant. Also, because we do quite a bit of multiple testing, it becomes harder to get a significant result. Okay. Yeah, in the postdoc there are now tabs for each interaction. So we have nitrogen, phosphorus, and potassium. And we can even consider the combination of all three. Let's see. Oh wait, am I going back now? Okay, so yeah, if you run the postdoc analysis, you get this very big table, and I see that now that not even everything is put on the slide. But what do all these numbers mean? Well, basically this is just nitrogen and nothing else. This is just phosphorus and nothing else. This is both nitrogen and phosphorus. This is just potassium and nothing else, and so on. So that is how you read them. And for each of these values, you have a difference and a confidence interval. And once again, you can look at the p-value, or you can see whether 0 is within this confidence bound. Another way to show this interaction effect is by looking at box plots. So you don't necessarily need to provide a box plot if you're performing an analysis like this, but maybe it is a nice way to visualize it for yourself. So, for example, it could be that two groups, so these two groups do have some difference, but this difference between depends on what other group they're in. So for example, if this is sex and this is two types of a treatment, then the effect of the treatment depends on the sex that you're in. So that is a way to visualize interaction. And if the difference between these differences is the same, then there is no interaction. But if there is a difference in differences, then there is an interaction. Okay, so just a quick summary. The one-way Anova is a method for comparing the means of one categorical variable, and a two-way Anova is a method for comparing the means of two categorical variables. If you think factor level combinations differ, you can also include an interaction. And a multi-way Anova is for comparing the means of any number of categorical variables. It also allows for interaction. Okay, so that was the end of this part, and that also concludes the end of this lecture. Are there any questions? No? Well, thank you very much for your attention. Frans, do you still have something to say?
Yeah, I will quickly share the assignment.
Okay, great.
Okay, so the assignment for today is again on the website. It's also on Brightspace, a link to here. Now we're going to chapter 6. In chapter 6, I go over the different parts of the lecture and ask questions pertaining to that part. So first it's only about one-way Anova, to make sure that you at least understood it up to there. Second part, we're going to look at how you can interpret the output. Yeah, and if I delete a couple values, are you able to calculate them? Third part, we're going to look at two-way, multi-way, and interaction. If you think interaction is difficult, I mean, it is. And we will talk about interaction a lot more during all the lectures about regression and GLM. So try to understand it. Try to understand the concept that the effect of one variable depends on another variable. That's interaction. But yeah, if you don't quite get it yet, don't worry about it too much, because we will be talking about it a lot more next week and tomorrow maybe. Yeah? Are there any questions about the assignment? If not, then good luck with the practical. Okay, I'll end the stream, but if you have questions, you can post them on Brightspace.